Questions? That means there's a floor. That means that there's a number that your sequence would never go below. Bounded sequences. A sequence is said to be bounded if, what do you think?
It's between.
Sequence is said to be bounded. We just talked about bounded above and bounded below. Those are two separate ideas, right? If we say that a sequence is bounded, what do you think that means? Both or one? What do y'all think? What seems more natural to you? Both? That's correct. If it is both bounded above and below. No, because you don't have to approach it. I'll give you an example of one that's bounded. I'll just write it up here real quick. Here's an example, a couple of examples. A sub n is 1 over n. Is that sequence bounded above? So just write out a few of these and you can convince yourself of it. 1, 1/2, 1/3, right? Is it bounded above? Okay, give me an upper bound. 2, give me another upper bound. 5, another one. 10. There just has to exist one number. It doesn't matter if there could be an infinite number of numbers, but if there's one number it never goes above, then it's bounded above. Okay, is it bounded below?
Yes.
By? 0. 0 is a lower bound, right? Give me another lower bound. -1, right? You see? That sequence is stuck between two things. So it's bounded. Agreed? Does it converge? What does it converge to? 0. So I wonder if a sequence is bounded, I wonder if it must converge. Give me an example of one that doesn't. Sine. Okay. I could do sine n, right? That'd be a bunch of dots and they'd be scattered back and forth. Is it bounded above? Sure. 2, right? Bounded below? Sure, -2. So these are two examples of two sequences that are both bounded. So they're both bounded above and below. One of them converges, one of them doesn't. Right? This one converges. This one diverges. I wonder if there's one, maybe there's a condition you can add that would force it to converge. So like if I told you a sequence was bounded, maybe there's just one more thing I could impose on it that would force convergence. I'll give you a hint. It has to do with exactly what we were just talking about.
Put it over in.
No, not that one. Not that one. Okay, so I'm trying to convince you right from these two examples that just because a sequence is bounded, that does not force convergence. Is there something you could impose on a sequence, a condition, on top of being bounded that would guarantee convergence? That would be an example, but I'm saying if I say that it's bounded, that's not enough. I have to also impose one more condition.
It's either continually increasing or continually decreasing.
If it's increasing or decreasing. Like what if I tell you it's bounded, but it's increasing? Or the other way, bounded and decreasing. What is this one? Is this bounded? Is it increasing or decreasing?
Decreasing.
It's decreasing, right? And it converges. Is this one bounded?
Yes.
Is it increasing? No. Is it decreasing? No. It switches back and forth. So maybe all I need is the increasing or decreasing to force convergence. And what do we call it if it increases or decreases? We call the monotonic. Well, that's exactly what you need. And that's where the next theorem comes from. It's called the monotonic bounded sequence theorem. Theorem 11. Out of the book, it's theorem 11. The monotonic bounded sequence theorem. And it says this: every bounded monotonic sequence does what? Converges. Every bounded monotonic sequence converges. So that means if somebody gives you a sequence and they want to know if it converges, and you try all this stuff and L'Hopital doesn't work and all these things and you just can't get it, squeeze theorem, you can't squeeze it, then if you can show it's bounded and you can show it's monotonic, you've shown it converges. What you don't show is what it converges to, all right? But you know it does converge. Now that's a big deal, because in everything that I've done up to this point, if it converged, we knew what it converged to, right? Yes? This theorem says you would be able to determine convergence, but not what the actual limit is. Should we see one of these in action? All right, so here's the way I'm going to do this one. I think I want to pull one out of the book for this one. How about a sub n equals 5n minus 1 over 4n plus 2. Now, here's the question. I'm not asking if this converges, all right? This does converge. You could just do L'Hopital on that one time and you're done. But here's what I want you to answer. Is this bounded? Is this monotonic? And then, how would you show each of those? So think about it for about 20 seconds. I'm going to just fill this with water real quick. Having that panic phone thing. Okay, there we go. All right. What do you think? Is it bounded?
Lower bound is 0.
Lower bound is 0? Okay, so here's the thing we have to do. we cannot, there's some things we can just say are obvious. Other things we have to show. In this problem, we need to show everything, all right? We can't assume anything is obvious. So you believe it's bounded below? And you believe that the lower bound is what? Little m is 0. That's what you think, right? So what I need to do is just show that that's true. I want to show that 5n minus 1 over 4n plus 2 is what? Bounded below means that this thing would need to be, how, in what relationship with that? Bigger than, right? Bigger than 0? Is that true? Is that true for all n? Okay, so how do you know? No, don't plug in numbers. Got to do it algebraically. So can I multiply both sides by 4n plus 2? Yes? Is there any jeopardy of flipping the inequality when I do that? No, because 4n plus 2 is positive, right? So I multiply both sides and I get 5n minus 1 is greater than 0. That true? Now I think we all could agree that that's always going to be true, but I'm going to go even further. 5n is greater than 1. Do you agree with that? Okay, let me go a little bit further. N is bigger than 1/5. Do you agree with that? Dividing both sides by 5. That one I think no one's going to argue with, right? Because what does n start with for a sequence? 1. So that's true, right? So you started with, this is what you thought was true. This is showing algebraically, yes, you are correct. Because n must be bigger than 1/5 for this to be true, and n starts at 1, so we're good. So it is bounded below. Check. All right, what else? Bounded above? You have an upper bound for me? Not sure? You don't think it's bounded above? What do you think? Do you think it is or no? No? Yes? I think the top and bottom both go to infinity, right? Why don't you start writing some terms out and see what this thing does? Okay, what did you get? 4, 6, 9/10. I'm hearing so many different things. 14 over 14. Okay. I'm not reducing any of them. I'm keeping them all like this. 19/18.
Yeah, that's where I stopped. And then I didn't go further up.
Yeah, because it got bigger than 1 there, didn't it? Like 19 over 18 got bigger than 1. Does it? 24 20 seconds. It is bounded above. Well, that's okay. I didn't ask you in the problem to figure out what this went to, but you can use that to figure out that it's bounded above. Look, this goes to 5/4. Doesn't it? That's the limit as you let n go to infinity, because you get infinity over infinity. You switch it to x. 5x minus 1 over 4x plus 2. You do L'Hopital's rule one time. Derivative of the top would be 5x. Derivative of the bottom would be, sorry, not 5x. 5, and derivative of the bottom would be 4, and you get 5/4. That's your answer. So this is approaching 5/4. So there's an obvious upper bound. You could use 5/4, but just go a little higher than that. 2. Here's my question. I think it's 2. I think 2 is an upper bound. So what do I need to show? I must show that the sequence is always less than 2. Now the algebra here is going to be a little bit different than the algebra here. You know how I wrote show? Like I want to show that this is true. In math, we don't write show, we'll do this. WTS, which is want to show. Okay, I want to show that this is true. I want to show, I know there are some math majors in here, and you'll thank me one day when you're like, I've seen that stuff before. Because you read a math book, and it's a bunch of these weird math symbols you've never seen before, and all of them are just short notation for abbreviations for. Oh, yeah? Oh, yeah, well, lazy. It's to make it look complicated, actually. It's a language. It's a language, that's all it is. Okay, so you ready? I'm going to do some algebra. I'm going to multiply both sides by the LCD. When I do that, do I have to worry about flipping the inequality? No. And what you're going to do here is go until you are convinced. And what I mean by that is until we are all convinced that there's no arguing about whether or not that's true or false. So let's distribute 2 through 5n minus 1 less than what? 8n plus 4? You're convinced? Yeah, but you could go a little further. How about this? 5 less than 3n? Is that right? Negative 5, yeah, sorry. Now? Just move the 4 over here, move that over here. This, right? Yes? Divide by 3? Say again? So this is going to be true as long as n is bigger than negative 5/3. But n starts at 1, right? So that's always going to be true. Is the sequence bounded?
Yes.
Yes. Okay. That was the first thing. Second thing, is it monotonic? Yes? You think so? If it's monotonic, that means it's either increasing or decreasing. Which one do you think it's doing? Increasing? 4 6, 9 tenths, 4 14, 14 14, 19 18. So it's getting bigger, right?
But what's it good?
Okay, so you think it's monotonic. You think it's increasing. Agreed? So what is it that you want to show to convince me that it's monotonic increasing? Or to convince yourself? Nope. Nope. What does the definition of monotonic mean? A sub n is less than a sub n plus 1. Right? That's what it means to be monotonic. Nope.
Because that's a sub 1 and a sub 2.
Nope. I'm only saying that to you because I can generate a sequence that will behave a certain way and convince you it's doing one thing, and later in the sequence it'll do something else. So, I mean, this is at the core of mathematics. Just because something does something a billion times in a row, that does not guarantee that it's going to continue. There's a famous there's a famous set of problems that were put out in, I think, the year 2000. The Clay Institute put these out. They're $1 million math problems. There's 7 of them. If you can solve there's 6 left.
Someone solve them?
6? I thought there were 7. Anyway, well, let's not debate that. Each of these problems are $1 million problems. So if you solve it, you get $1 million. All right. One of the problems is what's called the Riemann hypothesis. Okay, and it was a hypothesis by Riemann. We talked about Riemann a little bit, right? And his hypothesis is, it's a conjecture. It's a guess. He believes that all the zeros to this particular function lie on a certain line. And we've had computers check that line and find billions of answers that confirm his hypothesis. But that is not enough to prove the hypothesis. To prove something is different than verifying it. Do you understand what I'm saying? So you can look at this sequence and go out a billion terms and convince yourself that it is increasing. But that does not mean it's increasing. You show this, then you can conclude it's increasing. All right? So let's show this. What is a sub n? Well, 5. It's 5n minus 1 over 4n plus 2. I must show that that's what? Less than a sub n plus 1. So what would the one right after that one look like? 5n plus 1 minus 1 over 4n plus 1 plus 2. That's what it would look like, right? Right? If I plug in 1 to this one, then the next one I would be plugging in 2. If I plug in 2 here, I'm being plugging in 3. If I plug in n here, I'm plugging in n plus 1 to this one. I need to show this inequality is true, which means at some point I need to convince you or convince ourselves that at the very end, like n is bigger than 0, we'd be happy, right? You all seem to not like this. All right, 5n minus 1 over 4n plus 2. If you don't like this sort of stuff that I'm doing right now, then you might reconsider being a math major if that's your major. 5 minus 1 is 4, because this is what math people do.
All day.
Well, when you're a student of pure mathematics, this is just one of the little things that you do. You always have to prove something is always true. It's never enough to say, oh yeah, the pattern looks good. No, it's no good. Look, I'll give you a real quick example. I'm going to define a function. F of x is 1 if x is not equal to 10 to the 250th power, and 0 if x is equal to 10 to the 250th power. All right? So this is what we call a piecewise function. This function, the value of this function is 1 everywhere except that number, 10 to the 250th power, which is a huge, huge number, astronomically. Shit, I don't care. If you want to challenge me, I'll just add more zeros, okay? That is a huge number, right? So if you graph this function, here's what it would look like. In both directions, it would go 1 in both directions until you get to 10 to the 25,000 power. And once you get there, to that, only at that one point, it's 0. It steps down at 0, and then it goes back to 1. So if you're just sitting there and you don't know this function, and you're sitting there looking at it, you're like, yeah, it's 1. I went out this way for a long time, and I went out this way for a long time. It looks like 1. Then you're basically wrong, right? You've assumed that this is 1 when it's not. It's not the identical 1 function. Does that make any sense? That's why following patterns doesn't really prove anything in mathematics, which is why the Riemann hypothesis is still open. Now, the chances are that it is true, but no one has a proof for it yet.
Have you ever tried?
It's very advanced. It's no, I haven't. No, it's beyond my expertise for sure, which is why it's $1 million question. It's why Riemann and hundreds, if not thousands, of other people have tried to prove it. So the thing is, with proofs like that, what it often takes is other branches of mathematics to develop. And then what you'll have is you'll have a theorem in this branch of math that you don't even realize is going to help in this branch. And so this mathematician that's focusing over here is like, wait a minute, I'm trying to do that. But I read this paper about that thing, and I can use that theorem here. So it's really a matter of like copying and pasting other people's theorems to create the theorem that you are trying to write. And that, I mean, we're talking about the field of mathematics, the actual subject is so narrow at this level where I've told other people about this. If you have a PhD in mathematics, and let's say you call yourself a number theorist, okay? So your specialty was number theory, you got a PhD in mathematics, and then you got a buddy who's a number theorist also. They have a PhD in mathematics. If you set each other's PhD dissertations next to each other, and you went and read your buddy's and he read yours, or she, or whatever, most likely you would not understand each other's work. It's that specialized, that two experts in the same exact field cannot read each other's work because it's just so specialized, if that makes any sense. So this question, this Riemann hypothesis, it's been attacked by many different mathematicians in many different fields. They'll get it eventually, but you've got to be willing to dedicate, your entire career towards it, and you may not get it. Yes?
So I read about one of those situations where Newton said the best way to stack oranges was some stupid pyramid shape.
Mm-hmm.
And 100 and some odd years later, someone proved it. And it took him 15 years to prove definitively the best way to stack oranges. How did that benefit anyone's life?
You're the ultimate skeptic. You have to understand, you have to appreciate what a proof is. That's all it is. I understand. There's a difference between application and, theory. It's you are to be a mathematician, you have to crave the actual proof of something. You have to want to prove it. If that doesn't satisfy you, there's no reason to become a mathematician. But see, what happens, in an engineering field or in computer science, physics, what happens is you often have the problem, the real world problem, and you turn to the mathematician for the formula, the equation that's going to work. But that mathematician needs to guarantee it's going to work. And it needs to be done in a way that even the mathematician can tell you, look, this will work with the exception of these conditions. Then this formula won't work, and we have another one that works in those conditions. So you need the mathematician for high-level physics and chemistry for the guarantee that it's going to work. If you lose sight of the theory and you never have the proofs anymore, then what do you have? How do you know what's true? I mean, there's obvious stuff like stacking oranges, sure, but I don't know if I'm making any sense. Yeah.
It's like the backbone in mathematics.
It's the computer analogy that I've talked to you about. If all we do is plug in, if all an engineer does is plugs the problem into a computer and it spits out an answer and they go build a bridge based on that answer, if that bridge comes down, somebody has to answer to that, right? The computer scientist is going to say, well, I plugged in this program. Who wrote the program? Well, some other computer scientist. Why did they put that line of code in there? It's wrong. How do you know it's wrong? Well, we eventually go back to the theory, right? The machine is just executing an algorithm. That theory is always based on some mathematics. And there's always going to be weaknesses in the programs. So we're getting too theoretical here. I need to finish this up. All right, I've cleaned this up. I've distributed through, right? And now you need to do your multiplication. So I'm going to clear out all fractions. So I'm going to multiply this side. And then distribute. Do all this foiling. What do we have here? 20 n squared plus 30n minus 4, so 4n plus, so 26n minus 6 less than 20n squared 26n? All right? 20s plus 8. Let's get all our stuff on one side. Actually, the 20n squareds cancel. 26n's cancel. And you get negative 6 is less than 8. I could move everything to one side if I wanted to, right? I could say 14, negative 14 less than 0 if I move the 8 over. All my n's are gone. What does this mean? Is negative 14 less than 0? Yes? That means the inequality was right. Was that the original one? No, this is it. When is this true? Is what we were asking, right? What makes this true? If negative 14 is less than 0, it's true. That's always true. that's always true. This is true for all n. All right, so this is our check. We have concluded it is monotonic. It's monotonic, it's bounded, it must converge. We knew it converged to 5/4, didn't we? Okay, but if you don't know what it converges to, then there's the approach. So I have about 10 more minutes, and you've got me on this. You've got me thinking now. All right, so look, this is a well-known formula. This is just extra bonus coverage, okay? This is a well-known formula that if you add up the first n numbers, instead of adding them up, you can just use that formula over there. So if I wanted to add, for example, 1 plus 2 plus 3 plus 4, we all know we could do that, right? Real quick, we could do 3, and then plus 3 is 6, and that's 10. So we know that that's 10. But according to this formula, right, the n here is 4, right? 4 is the last number. And so if I plug 4 into this formula right there, let's see what I get. What would I get? 4 times 5 over 2, which is 20 over 2, which is 10, right? So it worked, didn't it? That formula worked. Now I could try it for another number. Maybe I go out and I add up, let's just go one more. 4, let's go to 5. That should be 15, shouldn't it? Let's plug 5 into this formula. 5, 6, hey, check that out. 30 over 2, 15, it works, right? If you check this for the next billion numbers, it's going to work. Does that mean it's right? No. No. How do we prove that this formula is true? I am. Okay, so my question, what I want you to think about is what would it take to convince you that something is always true? And this is what's called, I'm just going to abbreviate it for now because this isn't a math class, PMI, the principle of mathematical induction. All right, so here's how it works. And let's just see if you agree with this. All right, just see if you agree or not. Let's say that I have a set of dominoes. Okay? And I've got this row of dominoes. Those are dominoes that are on the ground, okay? Got this row of dominoes. And we all know that if in the real world, if I have a dominoes, if I push the first one, and these dominoes go forever, never stop. If I push the first one, theoretically, they should all fall. Theoretically. But we know that they won't because sometimes they aren't lined up properly, and you may have a malfunction, the spacing's wrong. All sorts of things could go wrong, right? So what would it take for me to convince you that all dominoes must fall? Well, I could just go and check, right? Like the first one knocked over the second one. Check it, it worked, okay, go to the next one. The second knocked over the third. Check it, yes. But I would have to do that all the way, wouldn't I? So instead, let's see if this is enough to convince you. If I can show this. If you show 1, that the first domino falls. 2, if kth falls, then k plus 1 falls. I claim that that's all you need to show. And you tell me whether or not you agree. If I can show these two things, all the dominoes have to fall. Okay, so anyone want to challenge me on that? I'm waiting. No. Look, you have to be an ultimate skeptic. I give you a hard time about being a skeptic. You have to be a skeptic. You have to. You can't always just take things on faith. Come on. All right, so here's how I can guarantee. Let's say you come in here and you say to me, no, there's one of them out there that didn't fall. All right? Let's go ahead and enumerate it. Let's give it a value, a number. Let's say it's the nth domino. all right? Let's say it's the mth one. You're telling me that one didn't fall, all right? Now, I have to, let's say I've convinced myself that this is true, all right? I'm going to now show you why the mth one had to fall. First of all, the first domino fell, all right? If the first domino falls, it's falling, right? The next statement is that if the kth one falls, the next one must fall. So if k is 1, right, then 2 must have fallen, right? And then now you can start the whole process over. K2 is falling, right? Or the second one's falling, so you could say k is 2. And now the third one must fall. And then you could keep going until you get out to m. But showing these two is not easy. I have to show it holds, the first domino falls, and then every domino thereafter must fall. Well, sorry. First one falls, and then if the kth one falls, the k plus 1 falls. So do you want to see this in action on that formula? OK, I'll show it to you. OK, so I want to show that 1 plus 2 plus 3 all the way out to n is equal to n times n plus 1 over 2. I'm going to convince you that's true. Ready? Ready or not, it's coming. Sorry, this is not within the scope of the class, but all right, so first of all, I'm going to show this. Let n be 1. And you know what? Let's change the formula to k's, because it'll lie more in line with the k's I was using for dominoes. OK? K, K, K. All right? So let k be 1. Is the formula true? Is the formula true for k is 1? Well, what would this side of the equation be? 1. Does that equal 1 times 1 plus 1 over 2?
Yeah.
Yes? Is that true?
Yes.
So do you agree that that statement is true for k is 1? Yes? OK. That's the first domino falling. All right? Now, next step. Assume it's true for k. So now what I'm assuming is that the kth domino is falling. That kth domino could be the first one, but now I'm just assuming somewhere out there the kth one is falling. Got it? So what does it mean to assume that it's true? That means I am assuming that this is true. I'm assuming that that is true for k. What I now need to show you is that the next domino must fall, right? So I must show now, I want to show you that 1 plus 2 plus all the way out to k plus 1 should be equal to k plus 1 times k plus 2 over 2. So what that is this formula with k plus 1 replacing the k's. So this is a question, right? Is that true? Right, here we go. Ready? This is 1 plus 2 plus 3 all the way out to k plus k plus 1. Isn't that what that left side is?
Yeah.
What is this piece? That's the domino back here that I assumed is falling, right? So isn't this k times k plus 1 over 2 plus k plus 1? Did you all see that? Get a common denominator there. K times k plus 1 over 2 plus, how about this, 2k plus 1 over 2. Is that right? Put them together. Factor out of k plus 1. What do you get? And what is that? That's what I was trying to show you, right? Isn't that what I was trying to show you? So look, I've proven it. The first domino fell. We all agreed on that. When k was 1, it worked, right? Then I said, if the kth domino falls, the next one will also give me the same answer. So now you can go back and you can argue, but I can always now say, all right, well, let's start with k being 1. Guaranteed k2 is going to fall, then k2, 3. This is the way you show something works all the time. Very important. I mean, principle of mathematical induction is like one of the foundations of mathematical proofs. It's only one of many types, but it's powerful. Powerful. Sorry. Try your homework. Your homework is 5 to 32. What? Is that what I gave you? Yeah, just add on to it 37 and 39. So I'll just put it up here. It's 5 through 32 and then 37. Let's go 37 through 40. Page 434. Sorry about that mathematical induction, but anyone want a bonus question? Yeah? Okay. Use the principle of mathematical induction, okay, what I just did, to prove that 1 squared plus 2 squared plus 3 squared plus 4 squared all the way out to k squared is equal to, oh shoot. Hold on. Hold on. I know it's over 6, 2n plus 1. Hold on, n. What's that? I need to know what it is. Hold on. I'm ashamed of myself for going to the book here. Where are the common formulas here? I have to be sure of this. Hold on. Can't ask you to do a bonus problem if... There it is. Okay. That's what I thought, but I didn't want to put it up here. 2n plus 1. n plus 1 times 2n plus 1 over 6. And don't just go Google the proof. Try it yourself. So what do you have to show? It's true for k is 1. Assume it's true for k. Show that it's true for k plus 1. All right. Have a good day, everyone. Oh, sorry. Yeah, they're all k's.